Hey everyone, and welcome back to episode 8 of my logic and set theory series. Our goal for this time is to prove this should be the final video in propositional logic before we move forward into first order logic. But we'll be proving the extended completeness theorem. And the extended completeness theorem is actually very easy to write down. The extended completeness theorem says that sigma is consistent if and only if sigma is satisfiable. And I may not have defined sigma being satisfiable. I can't remember, but it's really simple. It just means that that there exists a model that models sigma. Okay? So, in other words, sigma is consistent if sigma has a model, right? So this is extremely important. So why, why is this very important? What does this tell us, right? So let's rewrite this in a little bit more comprehensible terms. So this says that a set of axioms is consistent exactly when there exists an object that satisfies those axioms. And hopefully you don't need too much convincing that this is an important statement to say, because if a set of axioms, right? So there's two sort of use cases. Like, say for instance we're talking about vector spaces, and we wrote down the axioms of a vector space, and we wonder to ourselves, well, how do I know that these axioms are good? Like, how do I know that I actually just wrote down consistent axioms? Well, this theorem says that it's sufficient to just all we need, it completely suffices to just show in a vector space, right? So if I write down the axioms of vector space, those axioms are consistent so long as vector spaces exist. And since we know vector spaces exist, we know those axioms must be consistent, right? And of course, the converse is if we're writing down axioms, as long as the axioms we write down are consistent, we don't have to fear that there may not be an object satisfying those axioms, right? Like, a possible fear is, I told you, okay, these are all the properties I want my object to have. And I check and I look, and I'm very certain that the properties I gave you are valid, that there isn't an inconsistency in the properties I gave you. But what if even so, nothing exists that satisfies those properties? And then all this math I've done has been talking about nothing, right? This theorem also says that that's an impossibility, that as long as the axioms are consistent, there exists an object that satisfies those axioms. And thus we aren't talking, as long as we're not talking nonsense, we're not talking about nothing. That's basically what this theorem says. So hopefully I've convinced you that this is very important, and we'll dive straight into the proof. And we will handle this direction first. And it will begin exactly as you might expect. So we're going to suppose that sigma is satisfiable. So, of course, that means let's let A be a model of sigma. And what do we wish to show? Well, we wish to show, of course, that sigma is consistent, but we'll actually show something equivalent to consistency. We wish to show that sigma can not deduce a contradiction. And as you recall from a handful of videos ago, this is the same as consistency, right? A system's inconsistent exactly when it can derive a contradiction. Right? So that was something we proved earlier. So this will work as long as we can show that this can't happen. And in order to do that, we'll prove a lemma. And the statement of the lemma is as follows. We will show that let me do the lemma in red. So we will show that if sigma can prove some statement phi, then phi is true in our model A. This isn't too challenging of a proof, so if you're up for it, this could be a good one to try to think about. How would we prove this lemma? So hopefully you had a thought about this, and I don't think this is definitely not trivial, but it's not too challenging, and I think you'll be able to follow this proof. Even if you didn't get it, I think you'll be able to follow this proof as I present it. And of course, we'll unravel this statement and use a proof. So, of course, let me change color just so we're clear that we're in the lemma. So since sigma proves phi, we have a proof of the form psi at 1 through psi n. That, of course, proves phi. And this isn't too important, but recall that the proof has to end by concluding has to end by concluding the goal, right? So we'll show inductively that, and then we'll show inductively. Here we go. Sorry, sorry about that. So we'll show inductively that each psi I is true in A. So if maybe I always like to stop and give a chance for people to think. So think through. Why is this true? Why is it true that if sigma can prove, of course, A is a model of sigma, so A is a model of sigma, and sigma can prove phi. So why is every statement in that proof also true in A? Well, we'll be breaking this down into 3 cases because, of course, there's 3 possible things from our definition of a proof. There's 3 possible things that sigma I could be. So let's see if, hopefully you remember them. So one thing is that, I'll try to pick a striking color. So case 1 is that sigma, or psi I is in sigma. But if so, then obviously A models sigma I. I mean, right, remember from the very beginning, the definition, A models sigma if A models every sentence in sigma, right? So, sigma is modeled by A if every sentence in sigma is modeled by A. So if psi I is in sigma, then surely A models it, right? And for point 2, our next case is that psi I might be a tautology, right? There's 3 things, right? So this is the second thing psi I could be. Psi I could be a tautology. And then, but if it is, then we proved in the regular completeness theorem that psi I is also valid. So it's true in every model, right? This is sort of just that we're proving the extended completeness theorem. If you remember, the completeness theorem way back a while ago was that every tautology is valid, right? So surely all of the tautologies are true in A as well. And finally, and this is where the actual induction occurs, the final possibility is that psi I was inferred by modus ponens. But if that's true, then by induction, we know two key things. By induction, we know that A models psi k somewhere else, and we know that A already models psi k implies psi I, right? So let's just quickly ask ourselves, is it possible even possible that A not model psi I? Right? That's the key idea, and I won't write this out. But remember, a long time ago, we did the whole the value of a statement. If you recall, we could always take a model. Models are just sets of sentence symbols that are true. So if you remember way back then, we talked about the value of a statement. Well, if we consider the assignment that A gives us on these two formulas, well, then we can figure out that if this was an if and only if we proved. I think we did this in the original completeness theorem, but we basically proved that the value of the value of any statement here is true, or A models any statement exactly when the value of that statement is true on the assignment that A gives us, right? So since we know this is true, since we know A models psi k, we know the value of psi k in the assignment given by A is true. And we also know that this is true. So it's just a very simple truth table calculation that if this is true and this is true, the value of this must be true as well. And as a result, it must be true in A. Right? So this is just coming from the truth tables of these statements, that I can always look at K. I don't even know what K is. It's probably very complicated. But since by induction, I already know it's true in A, I know that its truth table has to evaluate to true. And I know that the truth table of this statement has to evaluate to true as well. And then how on earth could this possibly evaluate to false if I already know two of the truth tables evaluate to true? So, I'm not writing this is fully formal, actually, but I'm not writing this out because it would take quite a while to, give me the assignment and then blah, 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 blah. But you get the picture that, you can't have these two things true in A, but the consequent not. So that actually, I'll draw my box now. That completes the proof of the lemma. So now is actually another good time. I'll come back up and we can look at the lemma again here. So take a moment. Why does this lemma... Or I'll even make a bold statement. This is just a corollary of this lemma. So why is that the case? Okay, so let's take a stab at that. Well, I claim the following: not P and P. And actually, I'll use the symbols we worked so hard to develop. So my claim to you is that this statement is a tautology. And we can see that very immediately. The center, not P and P, always evaluates to false, and thus the whole statement always evaluates to true. So, of course, it's also valid. And so A models this statement, but by a very similar truth table reasoning I used before, we absolutely know that A does not model, right? A does not model this statement. Okay, so let me speak through what I just said. So the point is, the negation of a contradiction is a tautology, and thus the negation of a contradiction is valid. And so in every model, the negation of in every model, the negation. Oops, I missed a knot here. Yeah, that goes there. So in every model, the negation of a contradiction holds, and as a result, this is back from video 3 where we did the definition of a model. That if you remember, we did the definition of a model, and we said that something models a sentence exactly if it doesn't model the negation of that sentence, right? Remember that? So we definitely know that A does not model any contradictions. And so we've actually just proven the contrapositive of this lemma makes this statement a corollary, right? So we've proven that if sigma can prove phi, then phi must hold in A. So if phi doesn't hold in A, we conclude that sigma can't possibly prove phi. So I'm actually going to now write the QED box, because we have shown what we wish to show. We have proven that sigma cannot derive a contradiction. So this is one direction. This is the direction that if some set of sentences has a model, they can't possibly be inconsistent. Because, and you can think of before we leave this away, I'll give some intuitive understanding of what all this nonsense means. You can think of this as basically saying that models are always consistent, right? Almost by design, models are consistent, and as the axioms are something tangible we can touch. The models aren't, but the models are always consistent. So if there is a model, you can't have an inconsistent model. It's just not the way we've constructed models to be. Okay, so that hopefully was that was one direction of the proof. And so now we're going to prove the forward direction finally. So the forward direction will begin as you'd expect, just like the other direction did. So suppose so we're going to suppose that sigma is consistent. No. Yes. Suppose consistent. Yeah. Okay. I got confused. So suppose sigma is consistent. So by Lindenbaum's, let sigma be a subset of gamma for a maximally consistent gamma. Okay. So remember, we proved that any consistent set of sentences can be extended to a maximally consistent set. So, if sigma is a subset of gamma, then yeah. Okay, you follow. I'm making one brief claim here. So I claim this, that if A models gamma, then A also models sigma. Why is that true? Think for a moment. Okay, so this actually just comes from the definition of a model, right? So something models a set of sentences if it models every sentence in that set. And since sigma is a subset of gamma, it's a stronger condition to model gamma than to model sigma, right? Because surely if every sentence in gamma holds in A, then so does, of course, then so too do the sentences that were in sigma to begin with, right? Okay, so let's write one more line. So it suffices to construct a model it suffices to construct a model of gamma, okay? And we'll do that. And I'll give you that model. Actually, this might be a fun one to think about, but this is pretty hard. What is the model of gamma going to look like? All right, so without further ado, let's take a stab at it. We're going to define this set. So A is going to be exactly the set of sentence symbols such that the symbol is in gamma. And Right, so it's exactly the sentence symbols that occur within gamma. Okay, so right, and remember remember a model is just a collection of sentence symbols, and we're just taking the ones in the model to be true and the ones outside of the model to be false. So this is basically saying, let's just assume all the sentence symbols that occur in gamma are true, and all the ones that don't occur in gamma are false. Well, I think you might have one concern, which is, what if gamma can prove some sentence symbol? It doesn't have a sentence symbol, but it has, Q, and it has Q implies P, right? Well, then I claim, I actually then claim that P must be in gamma. And why is that? Well, since gamma is maximal consistent, and gamma union P is consistent, then of course gamma union P is a subset of gamma, right? Coming from the definition, or coming from the fact that gamma is maximal. Why is gamma union P consistent here? Well, remember, if gamma union P is inconsistent, it can deduce a contradiction, right? But I can prove P, so I could take the proof of the contradiction and then just append at the beginning of it the proof of P, and thus I would get a proof of a contradiction in gamma contradicting its own consistency. So, and this is true for, I said for P, but this is actually true for any statement phi. So the point is, if I can prove phi, it's not inconsistent. If I can prove phi, it's consistent to assume phi. And since gamma is maximal consistent, it's closed under. So this isn't really even the proof. This isn't even really related to the proof we're doing right now. But I'll write this out because it's a pretty important fact. Maximal consistent theories are closed under deduction. Right? If I can prove something, if I can prove something from the premises in gamma, it must also be in gamma, because assuming that as well would still be consistent. Okay. So that's a kind of a whole aside. So let's hopefully that made sense. We can back out of this now and get back to the proof. That will be, it seems like I took a complete detour, but this sort of reasoning will be very important. So by induction, we show that that phi is in gamma if and only if phi is a model of A. Or fuck, I said this horribly. Okay, so by induction, we're going to show that a sentence phi is in our set gamma exactly when phi is modeled by A. And A is this thing we constructed up here. If you recall, A is this thing we constructed back up here by taking all of the sentence symbols that occur in gamma. So this is our next goal. Okay. Sorry for that brief cut there. So by induction, we're showing this, right? And this statement is actually exactly the definition. And I'll make the quick note. I'll write it down. This is exactly the definition of A models gamma. I keep writing sevens instead of gamma. I really like 7, I guess. So this is exactly the definition of A models gamma. Okay. So hopefully it's very clear that my proof is complete when I've proven this statement, and this is by induction. And it will be induction. It'll be a nice conclusion to all of the model theory nonsense, because it will come all the way back to the very beginning and it's going to be our last proof. A tear comes to my eye thinking that we're finally done with this, but it's our last proof by induction on the definition of this. So, it's the three cases. So if, or rather, it's the proof. It's a proof along the definition of a sentence. Okay. So case 1. If phi is a sentence symbol, trivial by construction. Right? We took A to be all of the sentence symbols. We took A to be all of the sentence symbols that are, in gamma. So clearly, if phi is a sentence symbol, then we've baked this in, right? Okay. So bullet point 2. If phi is not psi, if phi is not psi, then I claim that psi is not in gamma. And why is that true? Well, the point is, we know that psi is in gamma. Or let me change the color because I will erase this one. So we know that psi, or I keep saying this, phi. If phi is of the form not psi, we know that not psi is in gamma. And if psi was in gamma, then gamma could prove. Clearly gamma could prove psi and not psi. So that would contradict the consistency of gammas, right? So from the consistency of gamma, we know that it can't include psi, which because our inductive hypothesis is an if and only if, this means that A absolutely does not model psi. But now, so I'll write this out. I'll be all formal here. So this is from the inductive hypothesis. And then, of course, finally, right, from the definition of a model, if psi does not hold in A, then, of course, not psi holds in A, right? That's just the definition of a model we saw, a billion years ago. And lastly, this might even be an exercise at this point because we're so good at these proofs. You can just do this. If phi is of the form, get ready for it, psi and pi, well, then what? Of course, we know that... actually, this one is a little harder. This one's a little harder, and it relies on that nonsense, the non sequitur I gave you earlier. But if this is the case, then we have gamma. Of course, this means... okay, so if phi is of this form, then gamma, we must have psi in gamma, and we must have pi in gamma. Why is that? Well, I'll write this as an aside and erase it. But if phi is in gamma, then gamma can prove using phi. Gamma can prove this is true, and gamma can prove pi is true, right? We actually gave this proof as an example a lot of videos ago. That if you can assume this, if you assume that this is true, there's a very simple tautology to use with modus ponens, you can deduce these. And then by what we talked about, this implies this, right? Remember that aside I said where, if anything gamma can prove is in gamma, right? So since phi is in gamma, and phi can prove that psi and pi are both true, then they must both also be in gamma. But now, by the inductive hypothesis, but now, of course, by the inductive hypothesis, A models phi, and A models pi. So same proof from definition of a model. From the definition of model, that of course implies that A models psi and pi. And that is it. That's our big QED box. Because, I'll speak the conclusion out loud, but since we've proven this statement, which means we've proven that A models all of gamma. And of course, from this aside I gave up here, that also means that A models all of sigma. So that's actually the complete proof. And we've done both directions now. We're in the clear. We win. Huzzah. We celebrate. And there's not enough left for another video, so I'm going to finish this off. And next time we'll be talking about predicate logic. So the last thing I want to prove is something called the Compactness Theorem. And this will be barely a proof. This is really more of a corollary of what we just did. The Compactness Theorem says that if sigma is finitely satisfiable, or rather, I'll just say, I'll say it like this: sigma is satisfiable if and only if sigma is finitely satisfiable. And finitely satisfiable means every finite subset of sigma is satisfiable. And this is something I alluded to in the previous video, that this would be true. But to fully formally state the compactness theorem, we needed to prove the completeness theorem, or the extended completeness theorem. But this will continue off of reasoning that I actually gave in the proof of Lindenbaum's theorem. This is almost a lemma I used in Lindenbaum's theorem. It's just that the satisfiability, we didn't have the connection between consistency and satisfiability yet, but now we do. And every finite, remember, satisfiable means that there exists a model of it. So I'm claiming that a set of sentences, there's a model for some set of sentences sigma. Sigma has a model if every finite subset of sigma has a model. And that's actually a really big statement, because if I have a set of sentences, it's not easy to consider. If I have an infinite set of sentences, it's kind of hard to find an object that would satisfy them. But if I have what this is saying is that one approach I could take is just checking every finite subset and making sure that every finite subset has a model. So one direction of this is actually completely trivial. So if A models sigma, then A models every finite subset of sigma. So there's nothing to that. It's harder to be satisfiable. It's strictly harder to be satisfiable than it is to be finitely satisfiable, right? So that's the forward direction. I'll erase this all, and the last thing we're going to do for and this is it. This is the last thing we're going to do for propositional logic is the backwards direction. And backwards direction. This is a really fun one. This is that last proof we did. I think it's really cool, but it can be a little bit. It's long. It's a little bit nitty gritty. But this one's just clean and simple and great, and it's just a very easy proof by contradiction. So suppose sigma is finitely satisfiable. Or actually, this isn't even a proof by contradiction. This is a proof by contrapositive. Let me reframe this. So we will suppose that sigma is not satisfiable. And we will show that sigma is also not finitely satisfiable. So suppose sigma is not satisfiable. Well, what did we just prove? Right? What did we just prove? Then sigma is not consistent. And that exactly means that sigma can prove a contradiction. Let psi 1 through psi n be a proof of P and not P. And then let sigma, I'll call it sigma naught, subset of sigma, be the statements used in the proof. And if you wanted to be formal, you could frame this as if you take the set of sigma 1 through psi n and the intersection with sigma, and call that sigma naught. If you wanted to be all fancy, we could call it that set. But basically, we're just letting sigma naught be all the statements I needed in the proof. Well, then we're done, right? Because then clearly sigma naught is also inconsistent. If you recall, this is exactly the thing. I almost reproved the same statement. This is exactly what I proved when I was proving Lindenbaum's theorem. That if a infinite set of sentences is inconsistent, then there's some finite set of sentences. There's some finite subset that must also be inconsistent, and it's precisely the finite subset of things the proof of the proof of the contradiction actually relies on. So that means this finite subset is inconsistent. But again, what did we just prove? Now again, by the extended completeness theorem, that means this set is not satisfiable. And of course, we conclude from that sigma itself is not satisfiable, completing the proof by contrapositive. So I'll leave it there. That was a pretty long one. But we proved the two big ones. We proved the extended completeness theorem. I keep writing sigma instead. And we proved the compactness theorem. Now, I know this was a long video. It's probably going to be even longer. Or maybe not. I don't know. There was that really long one a while ago where we proved the completeness theorem, and now we're proving the extended completeness theorem, and it's long again. It's just the way things are. But I'll write this down. This is just we're in the clear. We're taking a victory lap now. There's nothing else significant to do. But this was the most important video. Without question, this is the whole point of everything we did up to this point. And if you actually track through, this could be, this is a fun exercise. If you track through this proof and understand it, you'll see that there isn't one thing that I talked about in this entire series so far. There's not been one thing I talked about that wasn't somehow applied in this proof. So really, all these theorems we've been proving, all of the definitions I've been giving, everything has been just the stepping stones we need to reach the extended completeness theorem. And in a sense, the extended completeness theorem is the goal of model theory, right? The hope is that I've developed something that allows me to translate consistent sets into objects that satisfy them. And we've completed that task. We've done it. We've proved it. And I think it's even a constructive proof. So I've shown how to do it. And of course, the compactness theorem is something very important as well. But it's a very important thing because it allows me to treat infinite inconsistency as finite inconsistency, which lets me actually make sense of inconsistency in the axioms, right? So what do we have left? what do we actually have left? Well, unfortunately, we did all of this in propositional logic. So we've proven propositional logic is complete. But propositional logic is useless. Because I can only model incredibly simple true and false things. I can't make a group. I can't make a vector space. I can't do anything in propositional logic, right? None of this is, I can't do any of that. So what I've actually done so far is completely useless. How do we fix this, right? Will we need predicate logic? And I want to end this video by introducing our next goal, which is something called Gödel's. Probably the one you haven't heard of. This is called Gödel's Completeness Theorem. And intuitively, it says the completeness theorem and remember, the completeness theorem was this one. Is still true in predicate logic. So Gödel's completeness theorem proves the completeness theorem of predicate logic. So the next thing we're going to do in the next video, we will develop first order logic, predicate logic. These are the same things. So we're going to develop predicate logic, and predicate logic will be sufficiently strong to prove anything we want. So we'll, goal 1 will develop predicate logic, and then goal 2 will prove the completeness theorem for predicate logic to show that we're still safe. We're gonna massively increase the complexity of everything we've been doing, and we'll end with Gödel's completeness theorem, proving that we're still okay, and we didn't make it too strong that everything we said is wrong, right? I'll talk more about this in the next video. I think that's it. I feel like there was one other thing that I had on my mind that I wanted to comment on, but I can't remember it, so I guess we'll end there. It's this. That's the, presenting Gödel's completeness theorem. This is going to be the end of this chapter, or whatever you want to call it, right? It's going to get really, and I'm going to try to simplify, but it's going to get hard after this. The basic structure of the rest of this, of the next while of these videos, will be proving the analogous theorems, Lindenbaum's theorem, the completeness theorem, the extended completeness theorem, the compactness theorem. We'll be proving all of these equivalent. Statements in predicate logic. So the structure, the format, the order in which we do things will be incredibly similar, but we're going to have to be so much more precise and technical to be able to handle the strength of predicate logic. So things are going to get a lot harder. So at this point, this is a great moment. You should review, and especially since we just saw a proof that used literally every element of this series so far, you should make sure you understand this proof. If you don't understand this proof, you're not going to understand the next one. So make sure you understand all of this model stuff. Make sure you're very clear and you have a really good understanding of, models, validity, totality, all these things, all these definitions we've been talking about, because they won't change when we move into predicate logic. So if you can understand the intuition and the definitions of all this models stuff, you'll be able to use that understanding to build an understanding in the model theory of predicate logic. But if you try to start from scratch in the next video, it's not going to go well, because we're still going to be referring to all these. I'm going to be assuming that you're familiar with all of these definitions, and that I can radically increase the complexity of them, and we'll still all be talking the same language. So hopefully that's just a word of warning. It's gonna take off in the next video, and I apologize for that, but it's the way math is. It gets hard, and especially when the name Kurt Gödel appears, it just gets really hard. So we're gonna get there, and either way, thanks for watching. This is still pat yourself on the back. We're through. We did everything we needed to for propositional logic, and we're moving on to part 2. So that's awesome. Thanks for watching, everyone, and I'll see you next time.